Alrighty, so carrying on from the previous video, we're going to actually start finding the distance between points on the Earth's surface. So different places on the Earth's surface, we'll find the distance between them using longitude and latitude. Okay, so we need to know a few facts before we get there. So on a flat surface, the shortest distance between 2 points is a straight line. So we know that, for example, if I drew a point just here and a point just here, the shortest distance between them is a straight line that joins them up like so. Okay, that's obvious to us. We've known that for a while now. But on a curved surface, this is our first time finding the shortest distance between those 2 points. So to actually be the shortest distance along a curved surface, we need to be on a line that perfectly matches the curvature of the sphere. Okay, so just like the website I showed you in class and in the previous video, what looks like a curved line on a 2D map is actually a straight line that follows the curvature of the Earth. So that's why we need to know about great circles. Because great circles have the same radius as the Earth, and therefore they match the curvature of the Earth, and therefore the shortest path between 2 points on the Earth's surface is along an arc on a great circle. So let's start using that information. First, we're going to do distance along great circles and meridians. So longitude and latitude are measured in degrees. So therefore, for distances along the surface of the Earth, we use the length of an arc subtended by 1 degree, and then multiply that by the number of degrees the arc between the 2 points actually travels. So that sounds like gibberish, doesn't it? What I'm talking about is if I take a cross section of the Earth, so I get a circle like this. That's not a circle, let's try again. Okay, that's a little better, isn't it? Okay, so I've got my center, I've got a radius here, r equals 6,371 kilometers. Okay, excellent. Now, what I want to know is, what is the arc length of an arc that's subtended by just 1 degree? Okay, so what I'm saying is, I've got in here an angle of 1 degree, and I want to find out what is the length of that arc there, and I'm calling it S. So the arc that from that point to that point. So obviously S, it's an arc, so it's part of the circumference of a circle, and the fraction of a circle that we're talking about right now is a 1 degree slice of a full 360. 1 over 360. This is just the work from exercise 5a, by the way, but applied to the Earth. So 1 over 360 times 2 pi r. Okay, so I keep that fraction the same, times 2 pi. And my radius here, we've said for the Earth, we assume that it's 6,371 kilometers. So let's work out what that answer is. 1 divided 360 times 2 times pi times 6,371. It's roughly 111.2 kilometers. So what we're saying is if we have to travel 1 degree of longitude or latitude on the Earth's surface, we are considering that to be 111.2 kilometers. So we use this fact to do all the calculations along great circles. So let's start using that now. Instead of doing this working every single time, we just use that fact. So that's what it says on this slide here. So when 2 places have the same longitude, which means they're vertically in line with each other, because the longitudes are the vertical lines, the up and down, north-south lines, we use this working. So let's just look in this green box here. The distance between 2 points in the same meridian is given by this formula here. Okay, so being on the same meridian, it means you have the same longitude. And that's the second number that you see in the coordinates place. Now, this information here that I'm drawing the box around now, let's just read that out and think about it. So for locations on the same meridian that are in different hemispheres, we add the latitudes together. And for locations on the same meridian that are in the same hemisphere, we find the difference between the latitudes, always subtracting the smaller one from the larger one. So we'll take a look at why that is when we do our next example. Okay, so here's an example. It says Beijing and Perth have coordinates, and they've given those coordinates to us. We want to calculate the shortest distance between Beijing and Perth to the nearest kilometre. So I like to draw a diagram when I do these questions. It's like I'm drawing a cross-section of the Earth diagram once again. Okay, so along here, this is 0 degrees in longitude, okay? It's neither north nor south of the equator, it's exactly on the equator. So both of these places have the same longitude of 116 degrees east, but they have different latitudes. The first point is they're different latitudes. So Beijing has this one here, has 40 degrees north. So what that looks like is that means it's here. It's 40 degrees north of the equator, which is what I'm drawing onto the circle now. Sorry for the spelling. Now Perth, it has a latitude of 30 degrees south. So if we draw that in, it looks like somewhere about here, 30 degrees south. So we'll label that as well, 30 degrees south, and that is Perth. Okay, so in order to work out the distance between those 2 points, I'm finding out what is the arc length between Beijing and Perth. So what distance are we traveling on the Earth's surface? It's an arc because it's on a great circle. So what I can do is I can find the angle. And when I say the angle, what I mean is the total angular distance between them. So that if I'm starting up here at 40 degrees north and I travel down to 30 degrees south, I have to travel 40 to get to the equator and then a further 32 degrees. So that's 40 plus 32 degrees. And that's 72 degrees. Okay, so you can see why when you're on different hemispheres like this, I've got one in the northern hemisphere and one in the southern hemisphere, I have to add the angles together because I'm traveling all the way up from the northern point, down to get to the southern point, or vice versa, traveling up from the southern to get to the northern one. Okay, so that's 72 degrees angular distance that we're traveling. So that means that the real distance in kilometers is going to be equal to, like we said before, 111.2 multiplied by that angle. Okay, because a 1 degree angle on Earth is 111.2 kilometers. So if we multiply by 72, we then get our answer. And it's 8,006 kilometers. So what we're saying is along the Earth's surface, there's 8,006 kilometers between Beijing and Perth, if you're traveling south from Beijing or north from Perth. So that's how you do one of these. Now let's look at distances on the equator. So what we've said about the equator so far is that the equator actually is a great circle as well, isn't it? Because the equator is around the widest point of the Earth. So it has to be a great circle as well. So that means we can draw another circle to represent the equator just like before. Okay, so here's the center, and it's like I've taken a left to right, a horizontal cross section of the Earth, and now I'm looking down on it from above. So I've got 2 points. I've got point A with a longitude of 30 degrees west, and point B has a longitude of 90 degrees east. They both have the same latitude here of 0 degrees because they're on the equator. So point A has a longitude of 30 degrees west. So let's just make sure we label this. This is the 0 degrees of the equator. We are west of that, so let's go to the left because of northeast, southwest. So 30 degrees west is somewhere about here. 30 degrees. Now point B has a longitude of 90 degrees east. So that means it's roughly here. 90 degrees east. So let's label both of those points now. 90 degrees east, that's point B, and 30 degrees west, that's point A. Sorry for the slide flicking that happens when I touch the screen. Now we want to find the distance between these 2 points, but we're finding it in 2 different ways. So the first one is if we fly east from A to B, and the second one is if we fly west from A to B. So let's do A first. We're flying east from A to B. So we're saying east is traveling in this direction here. So we're traveling from west to east. So if we travel east like that, as we can see, the angle between those 2 points is 30 plus 90. Okay, so the angle that we'd have to travel, the angular distance, is equal to 30 plus 90 degrees equals 120 degrees. Okay, so therefore the real distance, because this is on a great circle, is just 111.2 multiplied by 120 degrees. And let's see what answer we get. So that's 13,344 kilometers for A. All right, that's A. That was a nice and simple one. Let's have a look at B. Okay, so if it's 120 degrees in A like that, to get from here, going around to here, that's flying east. Now we want to fly west from A to B. So that means we start at A and we travel west along the globe. So we continue in the western direction and travel to here. Okay, so I could do two things here. I could label my 180 degrees here on the globe. And I could say, well, to get from my point A to there, I need to travel another 150. That's this distance. And then to get from there to this 90, I need to travel another 90 degrees. So I could add those two together like that. Or I can just see that because I've worked out this distance here, because I've worked out that distance, the remaining distance, so the remaining distance out of the 360 would be this here. So because I've already worked out that angular distance in A is 120 degrees, all I need to think about for the rest of it is 360 minus 120 degrees. So I could do either of those, and so can you, whichever makes you more comfortable. So here I'll say the angle is equal to 360 degrees, take 120 degrees, and that's 240 degrees. Wonderful. So now we can just do our distance because it's on a great circle. The distance is 111.2 times 240 degrees. And my answer is 26688 kilometers, 26,688 kilometers. So that was distances on the equator, and the example we did before that was distances along the same longitude. Okay? Now, those are the easiest versions of these questions. We'll take a look in our next video at distances along the same latitudes. So I'll just end this one here.